The next step that Jackson used a much more complicated way to develop the velocity for velocity. And unfortunately, as Jackson way obviously is more rigorous, but we probably don't have time to do that. Actually, both section 5 and section 4 and section 5 Jackson use a much more elaborate or maybe more rigorous way to derive these things. So probably stay with more simplified way to devise things, make it easier. Okay, so now we know how to transform vector, space-time for vector, and we want also to transform other quantity. That the first thing you can think of is the velocity instead of just the space, and you take the derivative, we get velocity. And the idea is the velocity itself will not be a full vector. The, the transformation becomes more complicated. But one way to construct full vector that related to velocity, what we call a full velocity, is instead of using uh, what the consideration in here, they like to consider it a increment in space, time, and transfer the increment according to Lorentz transformation and figure out all the transformation. We are using a simplified way, so we are saying that so if we already have this x for vector, we define a u for vector. This x is a for vector, but if we take a derivative with respect to the proper time itself, then this is also a for vector, because we already learned about that the proper time is invariant. So, so whatever you, this is basically the time, whatever, say a particle or a certain object that moving in a certain trajectory in space time. But whatever the proper time is the time recorded by a watch following this object, and this is absolute. So whatever frame you're looking at the watch of that object, it should be the same. So uh, this is oh, this is an invariant in itself. So if you take a derivative with respect to invariant, this is still invariant with respect to relativity. So if this is a four vector, you take a derivative with proper time, this will also be a four vector. Okay, so we'll go this route to get the velocity four vector instead of a more complicated way. Okay, basically now just substitute whatever we have over here. So dt tau of this four vector CT. Okay, and we remember that d tau is dt over gamma. Now gamma is the gamma of the velocity of that object. So whatever the velocity you want to consider, you consider gamma. And I think Jackson uses gamma sub u to indicate this is the gamma factor of that object. So minus u is the velocity of that object. Okay. So now this derivative is so dt tau becomes dt tau dt, which is 1. And now this space time is again the same c dt d tau dx dt. Just do a chain rule in your derivative and use this dt over d tau is a gamma. So there's a gamma here, so you can pull out gamma. Why there's a c? There's a c. Okay, see, there's gamma, this gamma. Oh, I mean, include everything. So this is just one, and so this is C times gamma, and this is gamma times this is dxdt is just the velocity or ordinary three-dimensional velocity. Okay, so that is the velocities for velocity. Okay, and so the transformation is that the first of all, the perpendicular unchanged of gamma u. This is more careful. This gamma u, u perpendicular. It's the same as gamma u prime. U perpendicular prime. So the perpendicular component of the velocity actually change, right? They are not unlike the spatial vector, the perpendicular like y and x, perpendicular to the z relative velocity of reference. That is unchanged, but for velocity it changed. Like we express that u prime, u velocity prime at perpendicular components as gamma u perpendicular divided by u prime. Okay, so that is not the same. The perpendicular velocity component actually changed. Okay, and so you have still have these two factors, and you can figure that out by the time by the other transformation. So the other transformation are just following the Lorentz transformation. So you see gamma u prime, and then gamma u prime, u parallel prime is now gamma minus gamma beta minus gamma beta gamma gamma u gamma u parallel. Okay, now this gamma is the relative based on the relative velocity. So you have the relative velocity k prime and k, so gamma is just the usual minus b squared. So it's different from this. This u is the velocity part, the particle, the velocity of the particle. So that depends on frame. But this gamma is this factor. Okay, and so now you all that you can all have all the transformation, but if you like, because there's some kind of unknown, you have u prime. If you can use this relation to substitute in here. If you want the right hand side to be k frame, like you can solve that. So gamma u prime is gamma. Okay, c is a c gamma u c gamma u and minus beta. There's another gamma. You can, or you go out this is gamma u c minus beta. Okay. I mean, if you like, you can substitute this one over here. Then this is so the denominator has a gamma u. I mean, of course, you want to divide it by c. Also, so you know, gamma you cancel with this gamma, and the rest is 1 minus. Oh, there's a gamma here. 1 minus beta. Okay, then the right hand side will be all the quantity in the k frame. Okay, so let's see if I got everything. I mean, Jackson used the other way around to express k in terms of k prime 3, but all you need is changing the relative velocity. We change the minus v, so that should be fine. So this is the second relation of 31 with you change beta to minus beta. That's this one. And the pine and non-pine just interchange. And then likewise, there's the first the parallel transform like similarly. So that should be the first equation. 11. Okay. So that is all this transformation. So the by this, you can figure out how to transform velocity. I mean, transform velocity the formula is more complicated than the Lorentz transformation because the four velocity actually more complicated. Four velocity actually not just the ordinary velocity, even the spatial part. You need to multiply by this gamma factor to make it everything more complicated. And you want to transform acceleration, that actually even more complicated. I think there's a end of chapter question. And Jackson asked you about the velocity transformation. I mean, you can figure that out, and there's more than one way to figure out the transformation of velocity. I used to post the solution for Jackson. So in that solution, I worked out the transformation of acceleration also. I mean, you don't have to use that. Those should be covered by most textbooks. Okay. I guess that's the end of I'm out. Okay, I finished at least 11.4. So we start from next section, 11.5 onward. Okay, yeah.